And then I lied. These are actually getting watched, though, so that's kind of interesting. I find it interesting that people are choosing to watch the office hours instead of coming to the office hours. It's unusual. Okay. And I'm sure for some people it's because they can't make it, but for others it's weird. Okay, so if we're looking at this again, I think what we can do is take that and just disembody it.
Yeah, that's what I usually do.
Perfect. You're saving yourself a lot of grief. Okay, so on this carbon, the heaviest thing attached to it is going to be this carbon because this
Yeah, with
carbon
that.
is attached to a fluorine, whereas the other ones aren't. So that's going to be number one.
Yeah.
Then this carbon, this carbon are all tied. They're all CH2s. This one's then attached to carbons with a fluorine. Makes it number two. This one will be number three.
Yeah.
This one will be number four.
That's what I have, but don't you have to flip it?
Okay, yeah, now I'm going to rotate it. And I'm going to rotate so that 4 goes where 2 is. And if 4 goes where 2 is, 2 goes where 1 is. And 1 goes where 4 was. And that's counterclockwise, so that's S.
Okay, I think when I just like did the shortcut, I must have messed up because like I labeled them all right. Like I had them all labeled
Good, so
like
what
in
you
that
did is
order.
you swapped these ones with using the shortcut.
Yeah.
So if we do that,
It's still okay. Yeah, it's still S. Okay, yeah, I see
that's
it.
R, so that
Yeah,
has to have been S.
yeah, I see that now. Okay, so I must have just did that wrong.
Yeah, okay,
Perfect.
cool. You did
And
everything
then
right, just in the last step you
yeah.
stumbled. Okay, perfect.
Okay, that answers that then. And then I have just a concept question. I can try to share my screen. I've never done
Sure,
that
I'll
before,
stop
but
sharing and then you can share.
okay. Okay, are you seeing my screen? It's just about I know you can't give us answers, but I just want to know if my logic is right. So on this question, after you do like the epoxide um like opening or the addition to it, would when I'm trying to clear the positive charge on the OH, would I use bromine or can I just use water?
I'm not sure you'll have a spare positive charge on the OH, but you can just use water. That's fine.
Okay. Okay, that's it.
Yeah. Yeah, I'll try and make you can almost always just toss in water, and if I didn't define something, I'm always going to accept it. I'm being really careful on the final to put those details in.
Okay.
Yeah.
And then my last question is just in one of the lectures I couldn't make it. And you talked about like a bonus question, but like a student had put it in the chat and you said, oh, like that will be the bonus question. And I can't find or I have no idea what it was. And like no one's been talking about it since. So I was just wondering if you could.
I can't. It was in that one lecture. It is in a recording. It is a pretty. It's going to be a 1 mark bonus. I
Okay.
think you will be fine. I think
Okay.
most of the people who go to it has been mentioned multiple times. So
Okay.
the concept. So this has been something I've repeated multiple times. So I think anyone who routinely attends the lectures or routinely watches the videos is just fine for the bonus.
Okay. Sounds good. No problem. Okay.
But
That
it's
was
one
it for
mark
me.
out of I don't know. I think we're crawling up towards 150 or so.
Okay. No problem. Thank you.
Rose.
Hello, can I share my screen?
Yeah. And then I'm gonna go to Brianna because she got bumped yesterday. Yeah, so you should be good to share.
Okay, so I get this because you said that chlorine is more electronegative, so it becomes the nucleophile, right?
Yeah.
Okay, but if I can find it here.
Here I fucked up.
Oh,
So I
okay.
think I've actually uploaded the correction, or if I haven't, I've made the correction, haven't uploaded it yet. There's no way to get the product using the chemistry. Well, there is, but you have to do a lot of steps. There's no way to get there from where we are.
Okay.
Yeah.
So it is the most
Yeah.
electronegative that becomes.
I just when I wrote these the first time around, I just had a brain fart for like a few months and was just getting them backwards, and I just haven't corrected them since actually the first year I'm doing that. So I'm really sorry. Yes.
Okay. Also, just for solvents, like, do we need to put that for like every reaction? Because I know sometimes like here, for example, you didn't put anything.
You can if they're relevant. I tend to avoid. I tend to. You don't need to. If I don't define a solvent, you can pick a solvent that makes you happy, kind of thing. That kind of works. But normally, if I don't include a solvent, I'm basically trying to simplify it by saying, look, whatever the solvent is isn't going to participate in a reaction. But you're
So
always welcome, as I think Iying or Carly just mentioned, you're always welcome to add water to just clean things up.
okay,
To
but
remove
we're not
protons.
required to put solvent
No, you're
unless
not required to put solvents.
even for like E2 and or like the substitution.
Nope. If I didn't ask for it, you're not required. Normally, I'll ask for the mechanism, and normally you don't need to provide the solvent for that.
Oh, okay, good to know.
You need to provide. If I ask you to provide the solvent, then you need to provide a solvent. But if I don't, then you don't.
Okay. And along the same lines, if there's no mention of like how many equivalents, do we assume that it's an excess and
Yes.
that both?
Yeah. And that's actually going to be in the instruction, the exam instructions.
Okay.
Yeah.
And then for infographic, just for citations, I want to make sure I do it properly. Like, are you okay if we just put like numbers in the infographic and then like have a separate doc?
Yeah, I don't care.
Okay.
Yeah. And I don't want to, like, chemists tend to use the American Chemical Society as our reference format, or as a Canadian chemist, I tend to. But if we were in Europe, I'd use something different. If I was in the UK, I'd use something different. And they're all okay, and I switch back and forth between them. So it's not like we're not like social scientists, which have you must use APA for everything, and if you have a comma out of place, I'm going to murder you. It as long as I can figure out what the hell you're talking about, where you got this from, I'm okay.
Okay, sounds good.
Yeah.
And then here, I get what's going on. You attack the H, but the other day in office hours, you said that if there's a halogen, you use the double bond.
Well, if there's an H halogen, a hydrogen chloride or something, you're using double bond.
Okay, H halogen.
Yeah.
Okay.
But these kind of chlorinations tend to do this. And I really wish I had a better reason for it than that they do. And this is one of those things where I'm going, I don't quite understand this as well as I think I do. Because this does this, and I can't precisely tell you why. Or like why they're behaving differently. And it's about bond dissociation energies mostly, but I'm not really satisfied with that answer.
Okay.
Yeah.
Can I ask you one more question?
Yeah.
Okay. I know you gave this answer in the yeah, but I want to see, could this work?
Well, you got to the same product. Okay, I want to see what you did. HBr. Sure, I'll give you that. Okay, well, I'm not completely okay. You plus, then you separate them and you treat that. Okay, well, I'm good with you. I follow you until the last step, because using the isopropoxide isn't going to kick out the OH minus. OH minus isn't a good leaving group. So if you modify your answer by treating that alcohol with one of those sulfonate chlorides, like sulfon. I don't know if you know what I'm talking about. We talked about tosyl chloride and mesyl chloride and trifluoride chloride, and what that does is it turns alcohol into a really good leaving group because it adds a sulfur thing to it. I'm gonna annotate your screen, okay? Why is my okay? I don't know what's happening here. I think my tablet has frozen.
So it has to be a good leaving group for it to be a leaving group?
Yes, otherwise it won't leave.
Oh.
All you're going to do is acid-base reactions in that. You will eliminate the bromine. That's fine. I'm good with that.
Okay.
But nothing else is going to be useful. Huh. Yeah, my tablet has completely frozen because I was like, I'm going to annotate this with my stylus, but it's not resetting. And what do I do? Okay. Yeah. So yes. So if you do something, you have to turn into a good leaving group.
And to do that, you said, wait, could we just use like water or?
Mesyl chloride. So I'm okay. I'm going to draw with my mouse, and I'm really. I'm going to use text. So if you had treated this instead with imidazole, imidazole, and I don't know if you can see this yet.
Is it in the chat or?
No, it's going to be on your screen.
Oh, I see it.
There we go. And so mesyl is chloride, sulfur, O3, CH3. Oops, I hit enter or something. So it's got a sulfur with double bond O, single bond oxygen to a methyl group. And that adds that sulfur onto that oxygen, and that makes into a really good leaving group.
Okay.
Yeah, so I think we saw those 3 or 4 different times during the course. I'm just rebooting my tablet because, yeah, that was weird. Okay, yes. So other than that, so other than not working on the final step, your answer is fine.
Okay. Which is like half the mechanism, but.
Yeah, but what I'm saying is there are other ways to answer this question correctly.
Yes. Okay. Sounds good. Thank you.
Rejoin this meeting. Okay. I think Brianna, I think you got kicked out yesterday, so.
Yeah, I know it's simple, but for some reason, no matter how much practice I do, I cannot do the LCAOs. So I was wondering if you can go over like a more complex one.
Sure. I can move through one pretty quick. Let's see. I'm just going to load this up. Sorry, it's just computer's booting.
But that's okay.
Sort of. We have limited time, and I don't want to waste time. Okay, so I'm going to share a screen. Okay. So, I don't know. What do you want? Do you want some triple bonds?
I know there was one in the practice exam, number 35. It had 2 double bonds, a negative charge, and then it just had like a bromine atom attached.
How about something like that?
That's fine, yeah.
Okay. So I think the first thing to do if you're asked to draw an LCAO, or a linear combination of atomic orbitals, means you need to know what the atomic orbitals are. So step 1, whenever you get one of these questions, is assign the hybridization to each of the heavy atoms.
Okay.
And what you might need to do that is you might need to draw resonance structures if you can't see it immediately.
Okay.
So maybe the first thing you need to do is draw resonance structures. The second thing you need to do is assign the hybridization. Then you just need to draw it.
Okay.
So what we can do, hopefully pretty quickly, is say that's going to be SP. That's going to be SP. Those two are definitely going to be SP2. Right?
Yep.
Okay. So that leaves the bromine and the carbon as things that we haven't assigned. Can you tell me what they are?
For the negative charge, I've kind of been having trouble. I'm not sure if I count that as like another bond or not.
Can it do resonance?
In this case, if it was SP2, then it would be able to.
Right. And if it was SP3?
No.
Right. So do you want to do resonance?
Yes.
Right. SP2.
Okay.
You're always going to do resonance if you can. The bromine's the same. It can do resonance. It's got that lone pair, just like oxygen, nitrogen. I probably should have stuck with fluorine. I'm trying to avoid the heavy atoms here, but it does the same. It does shittier resonance, but it can still do resonance. So it's also sp2.
Okay.
So once you assign all of this, and you can do this by either trying to draw the resonance structures and keeping track of that, or just do it like we kind of did here pretty quickly. You're now kind of off to drawing. And first thing, start putting in the carbons. So if I'm starting with these two guys here, this terminal carbon, it's got a hydrogen on it. It's sp, so it's got two sp things. They're opposite each other. One's binding with the hydrogen, one's binding with the next carbon over. It's got two pi bonds. One is in the plane, and one is coming out of the plane because it has to be perpendicular to everything else. And this guy also has the other pi bond, and I guess I have to cross hatch one of these to give it some shading. Probably should use a different color. So we've got that. Are you comfortable with what I've drawn there so far?
Yep.
Okay. So this one also has another sp orbital, and that's going to connect up to this carbon. Now this carbon, we know that it has it's sp2. So I'm just going to start by drawing sort of this three-leaf clover kind of shape.
Okay.
And I know that there's a hydrogen dangling off over here. Right?
Yep.
And for convenience sake, well, since everything else is in the plane, I know that my p orbital that's on it has to be perpendicular to the plane. And that's got a lone pair in it. And you can indicate that if you like. You don't have to.
Okay.
So that leaves us with this thing, and that connects up to the next carbon, which is this guy here. And again, it's also sp2. So again, we have that sort of that shape, and then we have the p orbital perpendicular to the plane. And it has a hydrogen on it, and it's connected up to the next carbon, which again is sp2 because we just decided that, so it's going to have this same shape and a p orbital perpendicular to the plane. So that's the only spot left. So notice that we have this huge chain of p orbitals perpendicular to the plane.
Mm-hmm.
And then we have a hydrogen over here. And then finally we have the bromine, and the bromine is also sp2. So again, same shape, same p orbital. And so we have this huge chain of p orbitals along the entire molecule.
Okay.
And in bromine, sorry, that's, I guess it does have a lone pair in the p orbital, and it's got lone pairs in each of these sp2 orbitals. Should we draw the electrons in the orbitals? I think you have to draw the lone pair on the bromine. Other than that, I don't really need you to draw the electrons in the orbitals. But the lone pair on the bromine matters, otherwise those orbitals look like they're not going anywhere or connecting to anything. So it's important to draw those in, but everything else, they're kind of connected. Could you draw, would it be correct? I think it would be correct if you wanted to draw, an electron in each of the or p orbitals that makes it all bond. It's not necessary, but it would be correct. I think it's important to draw the lone pair on this one because, again, we do have a lone pair there. It's negative, so that we do need to indicate. So lone pairs, yes. Other things, no, because the lone pairs occupy an orbital. Otherwise, it's not clear that this molecule as a whole is negative if you don't sort of have that in there. Otherwise, we assume that there's an electron in every one of those orbitals, as it should be. I don't know if that helped, Brianna.
Yes, it did.
Okay. Yeah, that lone pair is from a negative charge. That's why a negative charge on carbon. So iron gas is a lone pair for a negative charge. The one on carbon, yeah, it is, because that's what a negative charge on carbon means, is you have a lone pair sitting in an orbital. And if it can do resonance, it's in a p orbital. If it can't do resonance, it must be in an sp3 orbital. Okay. Did you have any other questions, or just the one?
Really quickly, I just wanted to confirm. I'm on SAS, and I know we have 4 hours for the exam now.
Mm.
So does that mean we get, with time and a half, we get 6 hours, or are we still following
You
the
get time and a half. You only get the time and a half correction to the 3 hours of the exam. The extra hours is I'm not giving extra time for uploading for people. But
Okay.
you'll get 4.5. So you'll get 5.5 hours if you have time and a half.
Okay, thank you.
Yeah. And I have all the SAS reports. I'm going to go in manually and give extra permissions to everyone on the SAS, so the Mobius won't shut you down.
Okay,
Down for that.
perfect.
Yeah.
Thank you.
That's the job for tomorrow, John. Yes. If and what I'm going to basically do is I'm going to make an announcement on this, but this Zoom channel is going to be open the entire exam. And so if anyone runs into a problem, like a logistical problem, I can assist with that by
Okay,
just being
thanks.
accessible. Yeah. So if for some reason something happens, you just let me know.
Okay, perfect.
Okay. Okay. So do we draw the lines? So Rose asked, or do we draw the lines connecting the p orbitals only for the bonds in the structure? If I ask you to indicate the bonds, then you do. So if I just ask for the LCAO, no other suggestion, we're done. But if I ask you to indicate the bonds, what you'd have to do is draw that this is 1/2 of a pi. The other half of that pi is down here. And then we have another half pi. We have another half pi. Because each of these lobes is half a pi, then we got a sigma, a sigma, 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 sigma. And then we have a 1/2 pi here, 1/2 pi here. And the other ones don't have bonds, but they could. You could have drawn a separate resonance structure. I probably shouldn't have drawn all these little lines and circles and things. It's confusing things. There. Yeah. So if I asked you to identify each of the identify the type of bond that's formed in each place and indicate it, this would be the complete answer. Probably writing 1/2 a little bit neater than me. Well, an MO diagram is something completely. Drawing an MO diagram for this will be a nightmare. I can't really imagine doing that. Yeah. There's too many bonds. I don't even know how you would start. This is kind of what we're working with and pretending it's a molecular orbital. Okay, cool. So it's a team of GAs. I'll be marking the exams. Yeah, like 12 of them or something. But I look over. Yeah, it's mostly that. We actually have a few extras. I'm mostly going to be looking over the exams, so we're just checking to make sure that they're being marked correctly and consistently. Yeah, the exam is from 6 to 10. Okay. Yeah, like there's always some. If this was a type of course where people answered every question very specific wrong ways, we could have a set number of marks for every single possible wrong answer. But there are millions of wrong answers for every question, so we do leave. It does come up to the judgment of the GAs on a lot of places exactly how many part marks to award. Okay, so Jafer, you're up next.
Hello, can you hear me?
Yeah.
All right. Can I share my screen for a sec? So for this one here, I was just wondering because the resonance here kind of confused me. Like, I know that this one here is obviously the worst resonance just because of the two negative charge right next to each other. But when I actually ran through it myself, when I started from here, couldn't you kind of move like this negative charge all the way up here? And then you'd also have a similar effect with like a
Well,
positive
so
and
you're
a negative?
stuck at that point because if you move the negative, try and move the negative charge up there to make a double bond with the oxygen. That oxygen's gonna make 5 bonds.
Yeah, but then couldn't this lone pair? Oh, is it sp3? The Me?
Yeah, that the oxygen's sp2.
Yeah,
But where would you move those electrons?
the Me.
But they can't go. But so if do you want to just stop sharing your screen for a second? Let's talk about this.
Yeah, for sure.
It's a really good question. So I'm just going to share mine. New screen. So cool. If you did that, you're in good shape, and we just need to discuss this detail here. So Me is CH3, right?
Yeah.
So if so this is sp3.
Yeah.
And it's already using its 4 orbitals. The oxygen is
Okay.
also already using its 4 orbitals. So if we try and donate into here, if the oxygen tries to donate into here, then it's going to be making even more bonds because then we'll have oxygen. I guess this would be negative if we keep track. What I'm drawing here is completely wrong, everyone. This does not exist because I've got 2 problems here. First of all, the oxygen's using 5 orbitals, which is impossible because it only has 4 orbitals. So it needs 1 orbital for each of these bonds. So it's 4 plus 1 orbital for the lone pair. And now my methyl group is also using 5 orbitals. No, it's using 6 orbitals. No, 5. 1, 2, nope, 6. 3 for the methyl, 2 for the bonds to oxygen, 1 for the negative charge, which is a lone pair. And so that would be a carbon with 6 orbitals, and that's impossible. It's only got 4 orbitals.
Okay, I completely missed the sp3.
Yeah. So you're screwed.
For sure.
You can't do that. So once the negative charge up here, it can't delocalize onto that oxygen.
All right, sounds good.
Yeah.
And then you covered this earlier. So it is the other way around. The electrons go to the Br.
Yes, on that one question, assignment 4 question.
Oh, I thought I was sharing, but yeah.
No,
the BRI.
Yeah. The electrons attack the Br. The iodine's the leaving. The Br is the leaving group. The iodine is attacked. Yes, and I've corrected that. I've uploaded a corrected version of that, I think.
And I don't think you did for this one. I think you did for assignment 2.
Then I will do that as soon as this course is over because I've corrected it here. I guess I just haven't uploaded it yet, or as soon as this.
Okay.
Or maybe
perfect. Thank you.
Going on if I can do 2 things at once, which I probably can.
Thank you.
Okay. That was assignment 4 where I screwed up, right?
For this one, I'm pretty sure it was assignment 3 solutions.
Oh, it's assignment 3 solutions. I screwed that up. Oh yeah, assignment 4 is another way I screwed up. But I've corrected that screw up. Okay, cool. So I think Eyeing, you're next. Or did you already go? You already went. I think Anita, my window is all messed up. Anita, I think you're up next.
Okay, hello.
Hey.
I'll share my screen.
Okay.
So just with like when you get a reagent that's charged like this, but not really like basic, and it's a tertiary carbon, would it be SN1 or bimolecular?
Well,
E2.
See that you have a basic conditions. You have the OFO minus. So you have a strong base present.
Oh, it is a strong base?
Yeah, any negatively charged oxygen or nitrogen or carbon is a strong base.
Oh, okay. Okay.
Yeah.
So then elimination.
Yeah.
Okay, cool.
And it's a good question. Cool.
And then you answer that one. And then this I think was in the textbook, but is this another way of making like a carbonyl? Like the oxygen attacking the positive?
Yes. Yes.
Oh, interesting.
That that thing that we actually drew up there at the front, the first thing you have,
yeah,
is called an enol, and it's really unstable because it's basic. It's not a resin structure, but it's in equilibrium with with that ketone kind of thing you have up there. That protein.
Yeah, because I like looked at this and I was like, isn't this like resonance?
Yeah, exactly. And it wants to become the ketone because oxygen loves making double bonds to carbon.
Interesting.
The third year or the third organic course is basically all about the chemistry of this.
Enols.
Enols. Yes.
Okay.
You can do a lot of stuff with enols.
Cool.
Yeah.
All right. That's all I have. Thanks.
Bennett. Okay, just absorbing. Jess. Okay. Jess might have stepped away for a second there. Megan?
I'm just observing as well.
Okay. Mariam?
Hi. Yeah, I just had a question about when we do hydride shifts and alkyl shifts, or if we had to, because I don't.
We're not doing hydride or alkyl shifts. We're going to pretend that those don't happen. We have not discovered that. It's just that's one more thing. No, we're not. We're not doing any hydride or alkyl shifts. If you do one, and it's correct, I'll accept it. But I'm pretending that that's a thing that doesn't happen for this course. And then you went silent again. Was that your question?
Oh, whoops, sorry. So I was wondering, is that different from a proton transfer then? Because I was just
yeah, because proton transfers are moving an H plus around between different oxygens on a molecule. Whereas an alkyl shift or a hydride shift is rearranging things on the carbon skeleton to stabilize the carbocation better. So that's they are quite different. Yeah.
Okay. Yeah. And I had another question. It was from assignment 4, question 2C.
Okay.
And it was the one with CH3 minus as
Let me open it up. I'm just gonna pull it up.
Okay.
Assignment 4 2C. Assignment 4 1 2C. Okay, it's S. I really messed up by putting 2 at the bottom of a page. Yeah, okay, so it's got a S minus CH3.
Yeah.
Okay.
And I was wondering, is that a good base or a weak base? Because when I searched it up, it was I think the opposite of what. Okay, actually I don't remember. Hold on. I think it said it was a weak base.
It's not it's not a really strong base, but it's still basic. So I think we're still going to be favoring E2 in this case over E1.
Okay. Why would E1 or SN1 not be an option for this question?
Because the E2 or the SN2 is faster. So basically, if you have something that's negatively charged, it generally wants to react. And E1 and SN1s normally occur when nothing else can happen. So like the E2 and SN2 are determined by, I have something that wants to react to become more stable. Mm-hmm. And overall, this reaction is going to trade an S minus for an I minus, and that's a good trade. Like I minus is more stable. So that's favorable. Whereas E1s and SN1s, normally everything's neutral. Everything just kind of stares at each other. Nothing happens until you heat the crap out of it, and then you can force something to happen. Whereas an E2 or an SN2, those react fast. It's not so much that the E1 and SN1 don't happen, it's that the E2 or SN2 happen first. Faster. And the E1 and SN1 happen when there's no E2 or SN2 because you don't have a very reactive anything in there. S minus is reactive enough to favor the E2.
Okay. So if you can't like eliminate, I guess, E2 and SN2, you would do those. But then in this case, it's tertiary, so you would do E2.
Right, because the SN2 is impossible. Yeah.
Even though it's a strong nucleophile, I think.
It's a strong nucleophile, but it's a tertiary center. It's basically impossible.
Okay.
Yeah.
Okay, because I was just thinking if it's a strong nucleophile, if it wasn't SN2, it'd be SN1. But
well,
E2
strong nucleophiles are also good bases.
Okay, yeah. Okay, that makes sense.
Yeah.
And then I had another question from I think assignment X.
Okay.
Oh no, sorry, it was assignment 1.
Assignment 1. Oops, wrong file.
Question 5C.
So okay, yeah, I don't have letters, but this is the LCAO, right?
No, this is okay. Wait, would you be able to share your screen? Because I don't have it.
Definitely
open.
can.
Okay. Thank you.
Screen 3. So this is assignment 1.
Yeah.
5.
Yeah. So it was the one with CF3.
Okay.
And I was wondering, how you like assign the partial charges.
Okay. I can definitely do that. I'm going to stop sharing this screen, and I'm going to start sharing from my tablet. Okay. So the question is, how do we, for the resonance hybrid, how do we assign partial charges? Okay. So the question we're really wanting to know here is about this double bond, because that's the thing that's going to do any resonance, right? There's nothing else.
Yeah.
And I want to know which way that breaks. Now, the first thing you look at is, okay, is there any kind of obvious resonance that we can do with it? That, like, can it participate in resonance beyond itself? And the answer is no, because sp3, sp3, these basically act almost as stoppers to the resonance system. There's an sp3 atom at the end. You can't go through it, so you're screwed. Okay. Now, both of those are secondary carbons. Again, no difference. So is there any difference? And yeah, the difference is this carbon here has hydrogens attached to it. This carbon here has a CF3. What does that do? Well, I know that the fluorines are each going to pull electrons away from the carbon. It's going to make this carbon delta plus.
Yeah.
Okay. That carbon is now delta plus and doesn't want to be, so it's going to pull electrons away from the next carbon. I'm just going to make that one delta plus.
Okay.
Because we're kind of playing a game of I have no idea. There's no game like this. It's kind of like a tug of war, though. This guy's desperate and is really positive, doesn't want to be positive, so it tries to find a way to be less positive. And a way it can do that is by polarizing this carbon-carbon bond and stealing negative charge from this carbon. So this bond isn't evenly shared between the carbons. It's more towards this carbon. More of the electrons are towards this top carbon because it makes it less positive. What we want to do is we want to distribute charge evenly over the molecule as much as possible. Like nobody wants to carry the charge. Everyone wants to share the charge with everyone else. So by stealing some negative from this guy, we can make ourselves slightly less positive, but at the cost of making this guy slightly more positive. Okay. So when we do that, now I think, which way do I want to break this double bond? Well, I don't really want to put a positive here because then I have a positive next to a positive. So I prefer to put the negative here, which means I have to put the positive here. Right?
Okay. Yeah.
So, but it's not a full negative or a full positive, so I would say that's the delta negative and that's the delta positive. So then if I'm drawing the resonance hybrid, there's no real resonance-based charge changes on all of this. You could indicate if it's not necessary, but this would be delta minus, this would be the delta plus.
Okay. Yeah, because I was just thinking, because then the carbon attached to the fluorine would be delta positive, so I was just assuming like the charges were alternating. So then the next one would be.
It would be nice if they could, but it can't.
Okay, that makes sense.
Next guy can't be negative because where would it get the extra electrons from? So it can be by pulling, like if I make this guy negative, then this guy can stabilize himself by pulling some of that negative charge towards him.
Yeah, okay.
Which would then allow this guy to pull some more of that negative charge. So we're able to kind of delocalize some of the negative electrons in this double bond up towards this carbon to stabilize the whole thing.
Mm-hmm. Okay. And then in this case, since the double bond can't do resonance, would you show it as like a solid line, or would it still be dotted because of the charges?
I'd accept either. I've drawn it dotted here. I would accept it as a solid line.
Okay.
Yeah.
Okay.
Because it's not like the double bond can do resonance because you can always draw the resonance structure. It's kind of a trivial resonance structure, but it is correct to draw that as the resonance structure. Like that's the resonance structure.
Okay.
It's not competitive, right? Like,
yeah.
This is by far the major resonance contributor. This guy barely, that's not really a good description of the molecule, but it does tell us which way the bond's polarized.
Okay. Yeah. And then I had a question for like equilibrium questions.
Yeah.
If you're determining which way it lies. So like it's just a general question. So if you were to like draw like like you're comparing two molecules and like the charged ones, and then you were to like when you did resonance, like you saw that in one of them like the charges were distributed among more atoms, would that be like a good enough reason to say, oh, this one distributes it among more atoms, so the charge is more delocalized, so it's more stable, so it lies that way?
Generally, yes. The only caveat I'm going to do is if it's among more atoms of the same type. So if one is able, so for an example where this you have to be a little careful is if I'm comparing that versus that. Now, this guy only has one good resonance structure, but it's a doozy. Like it's a really good resonance structure. This guy's got more because I can delocalize onto this carbon.
Yeah.
And I can also delocalize onto this carbon. So this one's kind of got two resonance structures. So if I follow just blindly what you're saying, then I would say that this is better than that, and that's not true. This is better because the atoms involved are better. The oxygens involved are better. But if I'm comparing this versus this, absolutely this is better than that because you have more atoms involved.
Okay, so for example, for the question in the assignment with the OME versus the NO2, could you say that because of the NO?
Yeah, I don't know which assignment question that is, but if you distribute it onto the NO2, if it's a negative charge, you can put it up onto the NO2, then that's good. And part of the reason there is because you have more resonance, but the other thing is you're able to put that negative charge onto an oxygen instead of onto a carbon. And so that's better. Yeah.
Okay.
So, yeah, you're right, but just be careful with making sure that you're you're absolutely right. Distributing the charge more is good always, but just make sure you're comparing apples to apples.
Yeah.
Because if you can put it onto a better atom, that's going to this guy over here, delocalizing that negative charge between two O minuses is better than being able to delocalize it over like 6 C minuses. Because yeah.
Yeah. Okay. Because for that question, I didn't get the resonance that you got, a couple of them, so I was just but I noticed that there was NO2, so I was that's probably better than OME.
Yeah, and you're right. For negative charge, it's probably better.
Okay.
You are going to need to be able to justify it if that was a question that you got in an exam, but you would, but yeah.
Yeah.
Your instincts are good.
Okay, because it said to justify your choice with drawings. So if I didn't get it and I just said, I drew some of them, and then I said that, it distributes to the NO2, would that be good enough?
I think
or would I have to
actually
get
show
those?
the key resonance structure with it distributed to the NO2, you will be getting full marks.
Okay.
Because that's the most important part of it.
Okay.
You kind of identified where it matters.
Okay. Yeah, I got the NO2. I just didn't get the one with the OME. with the other negative charge going around.
Okay.
So, okay, that's good. I think that's all.
Okay, cool.
Thank you.
No worries. We lost Sforty, who was here but is now gone. Oh, Sforty's back. Hi, Sforty. I think you're up next. I think that's it. Sforty? Okay, does anyone else have anything else? Okay. Well, that's... Oh, sorry, Dana, I missed your question. For mechanisms with HBr and HCl, even though they are Markovnikov, if it has an oxygen group with a positive charge attached to the carbon, that's further from the oxygen group because the oxygen is very electronegative. Let's be careful about... and I'll go back to Jess's question too as well. That's where I'll finish this. Let's be very careful what you mean about the oxygen with the double bond. So, if you have a molecule like this, and HBr, yes, oxygen is very electronegative, but oxygen donates by resonance. And that is a much, much better carbocation than having it on the other side, because now I've got an 8-electron oxygen. Everything's got its full octet. So in that case, you're going to put the proton next to that. Now, if the... Just so we can be clear, if the example is this, now the oxygen can't do resonance. So now you have the pure inductive effect. And yeah, the oxygen is pulling electron density away. So I want the positive charge down here, not up near the oxygen. So in this case, the induction takes over because there is no resonance. And oxygen is electron withdrawing just like fluorine, but just softer. Yeah. So resonance dominate. Induction is almost always withdrawing, because almost every element we use in organic chemistry is more electronegative than carbon. I think if you had a carbon beryllium bond or something, then induction would go the other way. Yeah, and resonance is always higher priority than induction, because induction is always partial sharing. Resonance is you make a new freaking bond. So induction is always I'm taking like 20% more of the electrons. Whereas resonance is I'm giving you 100% of new electrons to make a bond. So it's a much better sharing. Yeah, and that's why resonance is always higher on my priorities. Well, the bromine will come in and sorry. No, don't do that. There we go. The bromine will come in and attack the carbocation. That gets formed. Sorry, it does do something. I was just talking about the carbocation. I wasn't finishing the question. So Jess has a final question. If you have a moment, can you do a little recap on how resonance plays a role in determining SN1, SN2, E1, or E2? Yeah, I can. That's a really good question. So let's say we have a molecule like this. And let's say I'm treating that with... I'm going to give us a borderline agent. So bromine. And bromine is one of these... It's negatively charged, but the halogens are the only special negative charged ones because they are so freaking stable. So this could do E1, SN1, E2, SN2 based on the presence of bromine. I'm probably not leaning so much towards the eliminations because HBr is a strong acid. And unless there's a really good reason, it's probably not going to do an elimination. It'll probably do a substitution. But what we have here in this question is, what role does resonance play on this? So let's think about this two ways. Now, if we are going to do, like, we can look at this and think, okay, we got a secondary iodide. It's a really good leaving group, but it's on a secondary, and it's on a secondary position. Secondaries are kind of intermediate between tertiary and, well, they're not kind of, they are intermediate between tertiary and primary. If this was primary, it's much more accessible, and the carbocation that's formed sucks. But because it's secondary, we have this. Yeah, so we're going with this, and I'm talking a lot, and Carly is cutting me short and just telling what the answer is, which is, yeah, it's going to do an SN1, because when you make the carbocation, it's not just a primary carbocation, it's a carbocation in resonance, or secondary carbocation, it's a carbocation in resonance. And if we go back to the one lecture where I talked about the stability of carbocations and said, look, resonance is always better than tertiary, with the exception, just two exceptions, that and that. And as soon as you do any kind of substitution onto that site, it becomes better than tertiary. And we have substitution on that site. Like, we have this, but we have that extra carbon. So this is better than tertiary. Tertiary is good. This is even better. This is in resonance, but if you look at the resonance hybrid, you're going to want to keep that bigger delta plus on the secondary versus the primary, because it's secondary versus primary. And so your bromine nucleophile is going to come in at the secondary position. Okay. So resonance favors SN1s and E1s because of this. Now, where this gets tricky, I think where your question is going, and where I want, where I want to take your question, is, let's think about these two reactions. And I think this was on one of the Mobius assignments. It was something similar to this, as which one of these is faster. You're looking at these going, I've got a really good nucleophile here, got a strong negative charge nucleophile. I am looking at SN2 or E2. It is on my list of the most stick-like of the sticks, which is making me think SN2. I have a primary leaving group, and it's a good leaving group. So I'm thinking SN2. And now, which of these is faster? Well, they're almost identical, except this one has a double bond adjacent to it. This one doesn't. How does that matter? Okay, so here, when we were looking at resonance, we were looking at resonance of the carbocation. And what we were doing is looking at the stability of the transition state leading to that carbocation. And that's essentially what we're doing here, trying to figure out what was going on. Here, it's SN2. We know the transition state is going to be iodine leaving cyanide coming in. This shouldn't really have anything to play with it. But it does. And that's because you can imagine a resonance-like thing where we basically break that single bond. We have a carbocation here. It's a shitty resonance structure. But you can sort of think, hey, these electrons, really good leaving group. Theoretically, you could get something kind of like this happening. And so what's happening is, what this double bond being adjacent to this carbon-iodine bond is doing is it's weakening the carbon-iodine bond. So that carbon-iodine bond, it's not impossible for it to be broken just straight off. No, there's no way this one is going to break. That would be a positive carbocation, and that would just be shit. But this one is kind of a little weakened. So it's a little weak already coming into it. This one's still a full-strength carbon-iodine bond. And if I have the same nucleophile, and I have a choice between a weakened carbon-iodine bond or a full-strength carbon-iodine bond, I'm taking a weakened carbon-iodine bond, thank you very much. And so this is going to be faster. So here, we're not really looking at intermediate here. Up here with the carbocation, we're looking at the intermediate. Here, we're kind of thinking about how this resonance affects the stability of that leaving group. And by weakening that bond, it makes it a little bit easier. Okay. Thanks, guys. And I really appreciate those of you who've been, coming to office hours over the past month or so, with questions. It really helps me because it makes me think, and you can see that I often will go back and cover stuff in lecture that we talk about in the office hours, because I know you guys hate the online lectures. I really despise them. I get no feedback in the lecture. I have no clue what's going on, where people are struggling, and it's different every year, what people have trouble with. And so it's really helpful for me to have you come and ask these questions and go, oh, I did not do a good job with that. So thank you so much for coming to this and making this a whole lot easier for me to do this course. Good luck on the exam tomorrow. And based on these questions, you guys are in good shape. Okay. See you later.